Okay, so thank you everyone for coming. Today we're very happy to have Starkman visiting us from Case Western Reserve University. And before taking up his professorship he was a citizen. And before that, he was at IAS. And before that, he was a PhD student at Stanford. And he has worked on various aspects of chemical physics. Just mentioning a few, including cosmology, modified theories of gravity, and even black hole searches at the LHC. And today he's going to tell us about anomalies in our universe. So.
Well, it's great to be back here and see old friends and meet new people. I want to tell you about the ways in which the universe. We're used to hearing about the ways in which the universe is agreeing with all our theories and how wonderful our theories are, how everything is just right. And I want to tell you about ways in which, on large scales, the universe is being uncooperative and refusing to agree with our theories. And this is work that I've done over the years with a number of people. Craig Kopes at Case Western, Dragan Hutterer at Michigan, Dominik Schwarz at Bielefeld, and then various people who've passed through Case Western, Neil Cornish, David Spergel, Ichiro Komatsu, Francesca Ferrer, Amanda Yoho, and Pascal Vadravanga, who is a graduate student here. Okay. So when we look up at the microwave sky in the 1960s, this is what we saw. So this is a map of the microwave sky. You can tell that it's in galactic coordinates. This is the galaxy. This is the galactic center. Both sides of the galactic anticenter. It's very clear this is the galactic north and south pole. It didn't take 10 years before we were able to make a little more interesting map, but not that much more interesting, because this is presumably the Doppler Quadrapole, due to our motion through the microwave background. So that's about a part in 1,000 smaller, just a few milli-K. And then in the 1990s, we were able to make maps like this using the Cosmic Background Explorer, in which we're finally seeing, well, first of all, we're seeing the galaxy. But then we're also starting to see what are real fluctuations in the microwave background at the scale of micro-K. Of course, maps since then have gotten much better. In the early 2000s, we were able to start making maps like this, in which you notice we've sent our satellites outside of the galaxy, and we're able to get rid of the galaxy. So when these maps like this were first made, they actually came with little disclaimers, okay, that said, do not use these maps for research. Okay. Well, of course, people immediately went ahead and used them for research, which was okay because they were actually designed for research. The original purpose of these maps was not just as press releases, because people didn't want to have to explain the galaxy going through the middle of the map all the time. So they make synthetic out of multiple band maps. They made synthetic maps that eliminated the galaxy and just left as much as possible the microwave background, but also to do topology searching, to look for the topology of the universe. That was the original purpose of making these maps, which has a interesting CITA connection, which is that I'd say 80% of the people in the world who worked on cosmic topology spent some time here in the late 1980s and early 1990s, and we're at one single seminar by Igor Sokolov in about 1993 or 4. And anyway, so we have, using this map, and the limits haven't really gotten any better. We have really, really good limits on cosmic topology, so I'm not really going to mention much about that today. Okay. Now, maps have gotten better. We're able to make multiple different versions of these full sky maps. You'll notice one of the things, and one of the reasons why people said don't do research with such maps, is because you do see remnants of the galaxy in such maps. Okay. But really, it's amazing how much better this is than that Kobe map, in which it was very clear where the galaxy was. So what I'd like to talk about in these maps is not their small scale structure, and that's clearly where they have made huge improvements in angular resolution and signal to noise, but instead about the large scale properties of these maps. So I want to talk about alignments at low L and what I would call the full sky failure of statistical isotropy. I want to talk about what people sometimes call the low L problem, but which I'll insist is really a large angle problem and the vanishing of the two-point correlation function. And maybe, depending how long I end up going on, I'll talk a little bit about parity or the first peak, but probably I'll get there and say, okay, we've had enough, and skip over that. Okay. So when you see a microwave background sky like this, or like this, you know if you've gone to Cosmology Kindergarten that what you're supposed to do is expand it in spherical harmonics. Okay. So, and the reason for that is that the standard model for the origin of fluctuations tells us that the coefficients of those spherical harmonics, the ALMs, are independent Gaussian random variables, and that the statistical isotropy of the universe is reflected in the fact that the expectation value of any pair of them is 0 unless they're the same one. I should have a star on one of these. And it depends only on L and not M. So the sky is statistically isotropic and Gaussian random, and therefore all interesting information in the sky is contained in these CLs. So if we could just measure these CLs, we would know everything interesting about the physics of the early universe, or most interesting things about the physics of the early universe, except in models that try to complicate this by, giving us lots and lots of non-Gaussianity or other things. But to first approximation, all of the interesting information is supposed to be in these. So we can try to, and these quantities, which are properties of the ensemble and the expectation values of the ALMs, are going to be related to the properties of the measured ALMs. And here is an estimator of those. So the CL, an estimator for this CL, which is a property of the underlying ensemble, is the average of the squares of the ALMs. So that's probably well known to everybody here. And so we do that. We get these beautiful curves. I haven't updated this one because I'm interested in everything going on down here, not what's going on down here. And things have improved hugely up here over the last 10, 15 years. Okay. But the amazing thing is that we can get such a low dimensional fit, this line, to all these points and to all the points that keep going on beyond that. So if you're interested in large-scale physics, then the most interesting thing maybe is where this first peak is, because it tells us that omega is equal to 1 plus or minus 0.0x, where x is some number that depends on exactly what other data set you use and what version of WMAP or Planck release you use, or et cetera. So if you're interested in the universe on large scales, is there anything else interesting left to learn? And of course, if the answer was no, I wouldn't be giving you this talk. I think some of us were, well, I know that some of us were first motivated to think that maybe there was something interesting left to learn by these 2 points, which turns out to be a really silly thing to be motivated by. In particular because this point isn't that anomalous. It's inside this gray band, which is the cosmic variance error band. It's a reflection of our inability to predict exactly what value of CL we will have when we only have a sample, in this case of 7, or in this case a sample of 5. Okay. And so the smallness of this is actually not that unlikely. Maybe 10% of realizations of lambda CDM would have a point this deviant. Okay. In fact, you'll see other points here that are similarly deviant. Okay. So why should we be interested in this? Okay. And lots of hay has been made out of these points, including cover stories of Nature telling us that that this is an evidence for the existence of cosmic topology, all of which is terribly misguided. Okay. But nevertheless, it did get some of us interested in asking questions about the large-scale properties of the universe. Okay. So here is just a small list of ways in which people have gone and done that. And I'm going to focus for now on one of these. Some of these others are equivalent, some aren't. The answers may be correlated or otherwise connected to what I'm going to tell you. But I'm going to focus on these only because it's the way I've come to think about some of these large-scale properties. Okay. So multipole vectors. And this came out of thinking about the topology of the universe and trying to look for properties of a universe that has non-trivial topology. Okay? So in a universe with non-trivial topology, even though your metric is homogeneous and local and isotropic, your space is not. Right? There are special directions generically in your space. And so we wanted to know, how do you look for special directions? Okay? And so one thing we start to think about is, well, we know what are the directions associated with the Lth multipole. So how do we ask if multiples of the CMB are aligned with topology or if they're aligned with each other? So I don't know how to answer that question with the dipole because most of us don't think of the dipole in terms of the A1Ms. we think of the dipole of a distribution in terms of some amplitude and some axis. Okay? And so instead of writing the sum over m of a1m, y1m, I might write some amplitude, some unit vector dotted into the unit coordinate vector. And the advantages of that is this really is a unit vector. It transforms under rotations like a unit vector. This is really a scalar, this a1. And only a1 depends on the value of c1, what we might, the sum over m's of the a1m squareds. Okay. Now, round about, this is early 2000s, people started to ask questions like this. In this group, Doppler Quadrapole et al., they noticed, they measured the following thing. I've never understood why, but it is what they measured. They said, let's look for the axis that maximizes the angular momentum dispersion of the Lth multiple. So for each L, let's calculate, instead of the sum over m of ALM squared, let's calculate the sum over m of m squared ALM squared. And that will depend on what I choose to be my z-axis. Okay, so for the quadrupole, there'll be a particular axis that maximizes that. For the octupole, another one, etc. And they noticed that the octupole was unusually planar, by which they mean that that you could choose the n in such a way that that when you maximize this, when you chose that n, that most of the ALM, most of this delta L squared was in the A33. Okay? So that's what they meant by planar. Okay? And that the axis of the quadrupole and octupole were close to aligned. Okay? So that was kind of the first hints of this idea that maybe the low L multiples were not statistically isotropic. Okay? What we said is, well, hold on, here's another way of thinking about the directions associated with the Lth multiple. Okay? So instead of writing the sum over m of ALM, YLM, I could write a product of L dipoles. Okay? After all, an angular momentum L object is the sum of L angular momentum 1 objects. And so if I appropriately subtract traces, I can replace the sum over m of ALM YLM by AL times the product of L dipoles. Okay? And the advantages of those is those L different U's are unit vectors. Okay? They transform like vectors, and all of the information, all of the CL information should be contained in AL, the strength of the Lth multiple. Okay? So it's just a different way of representing the Lth multiple. And we were very happy. We thought this was a very nice way to do it. Turns out you can also do this much more cleanly if you just write this as the product of L directional derivatives of 1 over r evaluated at r equals 1. Okay. It turned out someone else had done this before us. You may have heard of him. His name is Maxwell, and this is how he thought about multiples. So what this tells us is that we can replace the 2L plus 1 ALMs by L unit vectors and one scalar. Okay? And what we have been told is that we should only be interested in the properties of the scalars, that the properties of those L unit vectors are completely uninteresting. And so we decided to look at them. Okay? So the quadrupole has 2 vectors. In other words, we can think of the quadrupole as defined by a plane. And the octupole has 3 of these multipole vectors, so you can think of it as 3 planes. So this suggests defining the perpendiculars, the normals to those planes, and we call those area vectors. So the cross products of these U's. So the quadrupole is a plane, the octupole is 3 planes, and we're just asking what directions do those planes point, and how plane-like are those planes. It turns out that the area vector of the quadrupole is exactly the same thing as the axis that maximizes the angular momentum of the quadrupole. Okay. And if the octupole is perfectly planar, in other words, if those 3 planes of the octupole are the same, are parallel to each other, then the octupole, that axis is the axis that maximizes the angular momentum dispersion of the octupole. So they have a relationship to the Doppler-Quadrapole, Tegmark, Hamilton et al. Axes. Okay, so quadrupole is 1 plane, the octupole is 3 planes. Those planes should have nothing to do with each other if the universe is statistically isotropic. Or at least the quadrupole plane should have nothing to do with the octupole plane. The octopole planes, it turns out that these things in a statistically isotropic universe will not be uncorrelated, but they'll be widely separated. So what do they actually look like? Here in a very old projection, so we've decided never to change this because then people will say you're changing what you do. Okay, so here is how we plotted this in 2002, 2003. Here are I'm going to show you the area vectors of the quadrupole and octopole and how they relate to various physical directions that might be associated with the experiment, which at the time was WMAP. Okay. So here, and I'm plotting it in both the north and southern hemisphere because I don't know which way to think of this axis as pointing, so I'll plot it in both hemispheres. This is the axis perpendicular to the plane of the quadrupole, so the quadrupole area vector. Okay, the kind of dark gray. The octopole has 3. There are those 3 black dots. Okay? This one, it doesn't look like it's close near these, but you can think of it as also sitting just over here. So it's easier to look in the south. Let's look there. 3 octopole area vectors, 1 quadrupole area vector. You'll notice that they're very close to each other. Okay? That's what it means for the quadrupole and octopole to be aligned. You'll also notice that the octopole area vectors are very close to one another. That's what it means for the octopole to be planar. Okay, so the octopole is planar, unusually planar, and very closely aligned to the quadrupole. In fact, the quadrupole sits almost at the center of, in some sense, of these 3 octopole area vectors. Okay. You'll also notice that I've put all sorts of dashed lines on here. So, as I said, first of all, notice that they are in a very small region of the hemisphere. Okay. They're also sitting right on the ecliptic, the plane of the solar system orbit, which might have something to do with foregrounds or with some sort of systematic associated with the data analysis of WMAP or Planck later. Okay. They're also very close to the dipole, the direction of the satellites are motion through the universe. Okay. And maybe to the equinox, which is here or here, which is where the plane of the Earth crosses the plane of the solar system, maybe to the south galactic plane. Well, one of them seems to be very close to the supergalactic plane, sorry. So what is going on?
So this is based on this is WMAP?
Yeah, it doesn't matter. I'll show you. We'll see. Okay, we'll see how much it matters. Okay. Now, the area vectors tell you about the orientations of these planes, these 4 planes, right? So there's 4 planes. They're all very close to each other. They don't tell you everything. In particular, you can imagine, suppose they were all exactly the same. I could just rotate around those planes. The area vectors don't tell you that. The multipole vectors do. So there's, in addition, some extra information. So on the principle that a picture is incredibly informative compared to all these words, here is a picture of the quadrupole and octopole. And I should draw another great circle. There's a great circle that basically goes through the centers of all these 6 extrema. You'll notice that there are 3 kind of stronger extrema, 3 kind of weaker extrema. And they're very well separated by this great circle, which is the ecliptic. So this doesn't look like a statistically isotropic distribution. But is it? Well, the probability of the quadrupole and octopole planes being as aligned as they are is somewhere between like 0.1 and 0.6%, depending on exactly what map you use. Given that the quadrupole and octopole planes, those 4 planes, are as aligned as they are, the probability that they would be essentially perpendicular to the plane of the solar system is 0.2 to kind of 1.5%, depending on exactly which map you use. Given that the quadrupole and octopole are as aligned as they are with each other and perpendicular to the ecliptic, the probability that they would then be pointing at either the dipole or the equinox is a few percent. Now, those were conditional probabilities, so I might want to multiply those, in which case I would get a number less than 10 to the minus 5. But I'm not sure if I'm supposed to multiply those. I'm not sure. These were all a posteriori probabilities. I'm not sure what to do with those, except to say that this doesn't appear to be. It's every time you look at the next thing about these, they appear to be stranger. So is this just systematics of WMAP? Well, it doesn't appear to be. So here are the quadrupole multipole vectors of Planck. Okay, so and of WMAP. Here are a number of different WMAP and Planck maps, MICA and ILC, the 7 and 9 year WMAPs. And you'll see that, for example, here, let's see. So here are multipole vectors. They move by a few degrees. The area vectors move by kind of even less. So here are those area vectors all clustered around each other. What about the octopole? Same thing. Right? These area vectors, they don't move very much. Okay? It really doesn't matter which map you use. There is a little bit of difference for the quadrupole about whether you remember or don't remember that you're supposed to subtract the Doppler contribution to the quadrupole. Okay? And there's been some debate about how to do that. The original Planck release of the quadrupole of their maps didn't subtract the quadrupole. Then if you can do, there's some complications into exactly how you do that. The interesting thing is consistently across all the maps except WMAP 7, there's a huge improvement in the alignment of the quadrupole with the octopole, okay, if you remember to do the Doppler quadrupole subtraction, which is the one thing we know is not cosmological. So if you take out that systematic, that the Doppler contribution to the quadrupole, you improve the alignments significantly. Okay. So what can explain this? It could be cosmology, but how do you connect them then to the dipole? So you might say, oh, isn't the dipole cosmological? And the answer is no. I mean, the dipole is a mixture of the Milky Way's motion through the universe and the sun's motion through the Milky Way, and a small contribution of the Earth's motion, or the L2's motion around the solar system. So the dipole is not really a cosmological thing. So how can it be cosmology? The other thing is, it's not clear, and this is something to keep in mind with any attempt to explain this, is that remember that first picture where the quadrupole was significantly less than the octopole. Now, that's a little bit misleading because we don't plot the CLs, we plot LL plus 1 CL. But the quadrupole and the octopole are very similar, and any explanation has to explain why the quadrupole and the octopole are similar in magnitude. And most explanations will be some sort of perturbative explanation, and when you dig into them, you discover that the octopole is epsilon times smaller than the quadrupole, where epsilon is whatever they're perturbing it. Okay, so that doesn't work. Systematics. Well, how do you get such an effect in systematic? And how do you get a systematic that appears in both WMAP and Planck, which have completely different approaches to measuring the CMB and to analyzing their data? So we have no idea how you could get this in systematics. People have said, well, it's the galaxy. But the problem is this has completely the wrong multipole structure for the galaxy. So one important thing, and for most foregrounds, which I'll mention here, is that most foregrounds, people will say, oh, well, there's a patch of the sky that's unusual, and that's what's contaminating it. The problem is that almost always leads to aligned YL zeros. So it leads to a Y20 and a Y30 with an axis through the patch that's strange. That's not what we see. We see a Y22 and a Y33. In other words, we see a ring of extrema, okay, that has a quadrupole and an octopole that form a ring, not a patch. Okay. That isn't anything like what the galaxy looks like. So it has the wrong multipole structure to be the galaxy. Okay. And besides, if it was the galaxy, you'd expect to get galactic and certainly not ecliptic or dipole or equinox correlations. Same problem with other foregrounds. Typically, if you change a patch of the sky, you're going to get YL zeros. The other thing is the sky has about 5 times more octopole than quadrupole. How do you get that is not what most foregrounds give you. You have to have something that has mostly octopole that leaks into quadrupole. Okay? How do you get a physical ring perpendicular to the ecliptic? Now, the only thing I will tell you is you have to be a little bit cautious when I say that it's a ring, because I don't actually know the dipole, which means I can change a ring into a long streak. So maybe it's a streak that happens to be perpendicular to the ecliptic just over the solar system that's lasted very cleanly for about 15 years and is much less than 30 degrees K, is just around 3 degrees K and just happens to be sitting there, unfortunately, contaminating our data. But then you ask, well, that means that most of the CL that we see has nothing to do with cosmology. Most of the C2 and C3 has to be from some foreground source. So that causes mysteries of its own that we'll come to in a minute. So, and how do you hide this foreground from detection? You have to make its temperature very close to that of the CMB. Okay. So we don't know which of these to prioritize. In other words, I don't know whether what's really going on is that the quadrupole is associated with the octopole, and it's just an accident that they happen to be perpendicular to the ecliptic. Or is it that the signal is perpendicular to the ecliptic, and that aligns them with the quadrupole and the octopole? Or is it that they're correlated with the dipole, which is sitting very near the ecliptic, and that's what's giving me some leakage somehow from the dipole into the quadrupole and octopole? We don't know physically what the explanation is for this, but it certainly does not seem to be statistically isotropic. Okay. So I've talked to you about the correlation. Now I'd like to talk to you about the uncorrelation. So I said that what was strange, what people noticed was strange, was this low quadrupole. So in fact, this is what got many of us, in some ways, interested in looking for the topology of the universe, because the idea was, well, topology was going to suppress long wavelength modes. If the universe is small, then it can't have modes bigger than the box, and that was going to give you a low quadrupole. For all sorts of reasons, that's misguided reasoning, but nevertheless, it was what got some of us started, so we were interested in this low quadrupole. What I'd like to suggest is that actually this arrow, which is pointing down to what L the measurements are at, should really point up to what angular scale we're making the measurements at. Okay? Because what's really strange is not the low quadrupole, but the two-point correlation function. So long ago, before people knew that what you were supposed to do is measure angular power spectra, instead we looked at angular correlation functions. Okay? So what's the angular correlation function? You take the temperature in one direction, the temperature in another direction, where those directions are separated by some angle theta, and you average over all such pairs on the sky. Okay? And that is C of theta. Now, the established law is that it doesn't matter whether you think about the two angular correlation function or the angular power spectrum, because they contain the exact same information, just differently organized. Because they're related by this, in exactly this very clear mathematical way, which says if I know CL, I know C of theta. So since I have really good theory of C sub L, why would I bother looking at C of theta? And that's actually what happened, is why people stopped looking at the angular correlation function between Kobe and, by the time of Kobe, they had kind of nearly abandoned thinking about this in favor of thinking about the angular power spectrum. Though on the one hand, this is true if C of theta is obtained by a full sky average. On the other hand, it's true in the ensemble if the sky is statistically isotropic, but I've just told you that on large scales it doesn't appear to be statistically isotropic. The other thing is, remember this thing called Fourier transforms, where sometimes you look at the data stream and you Fourier transform it? So even if that doesn't put more information into your Fourier transform that was in your original data stream, it just organizes it differently. So sometimes when we reorganize our data, we learn new things. So for example, Kobe, back in 1996, only in their 4th year paper, they decided to show the angular correlation function, and here it is. So you'll notice that in each of these bands, that above about 60 degrees, it's very close to 0. They don't plot on here what you'd expect, so let me show what you would have expected. Here's the 3-year W map data in various bands. The blue band is what you'd expect. And this is one of the difficulties of the two-point correlation function. So in the theory tells us what the expectation value of CL is and what its variance should be. And that can lead to a wide range of two-point correlation functions, which makes it harder to do the statistics of two-point correlation functions than of angular power spectra. But here is the band, and the first thing you will notice is that the data does not sit inside the band. That shouldn't bother you that much. It shouldn't bother you that much because you'll notice the band is wide, and and the errors are correlated, and I haven't told you how to compare these two. And so if you write down some reasonable norm, like the integral of c of theta observed minus c of theta theory squared over angle, for example, and use that as your measure, you'll find that this is unusual at the level of maybe 10%. In other words, 10% of all realizations of lambda CDM have the 2-point correlation function this different from the expectation. But what you should notice is that for most of these, for all but this solid black and this dashed green, and we'll come back to them in a second, that this is awfully close to 0. And so if you ask how often does the 2-point correlation function stay this close to 0 above 60 degrees, the answer is a much smaller number. And I'll tell you exactly how much smaller. But what I'd like to notice is the two different sets of curves. So this is a set of 4 curves that lie pretty much on top of each other, and a set of 2 curves that lie pretty much on top of each other. And the 4 curves are very 0, and the other curves are less 0. So what are the 4 curves that are very much on top of each other? Well, they are the for the Q, V, and W bands of WMAP, so the actual observed skies. Okay? You calculate the actual 2-point correlation function on the sky. In other words, you take pairs of pixels, and you take the products of their temperatures, and you average that over all such pairs of pixels. Then there's a synthesized map, that ILC map that I showed you for WMAP, where again, you only take the part of the sky outside the galaxy. So you cut out the galaxy, and you just do what I just said. You calculate the 2-point correlation function. But if instead, for example, you take the reported values of CL as reported by WMAP in year 3, and then use that formula to reconstruct a 2-point correlation function, you get something that's not quite the same. Okay? Or if you take the 2-point correlation function over the full sky, including the part behind the galaxy, where you don't actually trust the measurement, you get something identical to what you get from the CLs. So notice the cut sky gives you this. The full sky, or the full reconstructed sky, gives you something not quite the same. Small, but not that small. So WMAP created this statistic, the integral from -1 to ½ of c of theta squared d cos theta. And they said, only 0.15% of realizations of inflationary lambda CDM with the best fit parameters have lower S. Okay? And then it appeared that that went away after their first data release. Okay? What I'd like to point out is that it never went away. Okay? So in fact, if we look at that cut sky 2-point angular correlation function integrated from 60 degrees up, so on the full sky, it was always around 5%. Here's after 3 years, after 5 years. If I put 7 years and 9 years, it doesn't change, about 5%. But if I only look at the part of the sky outside the galaxy, the percent of realizations of lambda CDM that give you this little 2-point correlation function by this measure S1/2 is somewhere around 0.02 or 0.03%. And so it happens a few times in 10 to the 4. Okay. And that is consistently across those WMAP maps. Okay. Well, here's what's going on. Okay. So if you take pairs of points, both of which are anywhere in the sky, okay, so it doesn't matter where they are, you get this black curve. If you demand instead that they're both outside the galaxy, you get this red curve. So most of the observed 2-point correlation function on the full sky is due to pairs of points, at least one of which is inside the galaxy. Okay, so it's either galaxy-galaxy correlation or galaxy-outside correlation. So there seems to be something problematic with including, well, something different at least, whether you include the galaxy or don't include the galaxy. Okay. Now this could be an accident. Okay? It could be that you have, remember, this is still low. This is still rather near 0. But it's not that unusual. It happens, a few % of the time. And then if you're unlucky and you have that unusual few % of the time, and the sky just happens to be rotated in such a way that all of the correlations lie behind the galaxy cut, which happens about 2% of the time, then you can, in fact, get this little cut sky two-point correlation. There are two unlikely events. Or you require one very unlikely event, namely that, so if the cut sky is in fact suggesting what's really going on with the full sky, then it's, well, okay. So if we take realizations of lambda CDM and look at cut sky two-point correlation functions, that's what we're looking at. Not reconstructions, not attempts to infer the full sky. Just ask ourselves, if I make a full sky realization of lambda CDM, how often does the cut sky two-point correlation function give us this low a value? The answer is usually 0.03%, but on some maps, as much as 0.1% of the time. Okay. Does this change in Planck? Well, here's what you get if you do Planck. So these curves. Now you can't tell because I haven't compared them to WMAP, but here is comparison. Here are the WMAP, 9-year, the WMAP. So the dash curve is the black dash curve is the WMAP 9-year result, the blue curve and the red curve. So whenever we cut the sky with the dash curve, the black dash curve, or the dotted blue curve, we get something very near zero. When we look at the full sky, we get something near zero, but not as near zero. Okay. So no difference between the WMAP, so black and red, or black and blue. So it hasn't changed at all. It actually has gotten, if anything, a little bit worse. I don't know how much stock to put in this. So this is, as we make the mask get bigger, so the galaxy masks get bigger, we can ask, well, what happens? Well, in WMAP, this sort of bottoms out, this S1/2 bottoms out around 1100. And then if you start to exclude more of the sky, then this S1/2, which is this measure of correlation, starts to kind of goes up a little bit and saturates around 1300. Whereas with the SMICA map, at least it keeps going and going down. Now, this does make a few point, like a 0.1% difference in exactly what the p-value of this measurement is. But so between here and here, I think this is 2 times 10 to the minus 4. I think this is 5 times 10 to the minus 4. All right. So how weird is this? And the answer is it's weirder than you would hope. Okay? And what I mean by that is you would hope that the simple explanation would be, okay, so my standard inflationary model made a slightly wrong prediction. I'll just change the inflaton potential a little bit. So I'll get I'll predict the right CLs and everything will be okay, right? But it doesn't work that way because there's huge cosmic variance on the CLs. You can change your CL predictions. It will not help you get a small two-point correlation function because what we learn is that in order to get this little two-point correlation function, you actually have to vary together C2, C3, C4, and C5. Okay. So one way to look at that is the value of S1/2 on the sky is about 1,000. Okay. So in the theory, so if we took the theoretical CLs and just changed C2, okay, we could get the predicted value of S1/2 down from about 7,600 to about, down from about 50,000 to about 7,600. If we played with C2 and C3, we could get it down to about 1,000. We'd be happy. So all we would have to do is lower those. Okay? And that's just by adjusting the CLs. You'd say, oh, that's going to work really well. In fact, with the observed values of the CLs, you have to play with C2, C3, C4, and C5 in order to get this low a value. And what's wrong with that is that let's suppose you predict a particular set of C sub Ls. So here's the old theory, here's the observations, and what I do is I say, okay, well, my old predictions, I'm going to move them all onto exactly whatever I saw, and so that will give me the expected value of C of theta is, integrated squared d cos theta from -1 to 1/2 is exactly what I saw, 1100. You do that, and now so here's my new prediction. Very good. It turns down like this, and this gives me the right value of S1 half. And now I go and make a realization of this theory. Okay. Well, the cosmic error band around this is like this, around this is like this, around this is like this, around this is like this. And now I do realizations of the CLs that are independent, and the first one's here, and the second one's here, and the third one's here. And now I end up with an S1 half that's, again, more like 20,000. Okay. So it doesn't work. If these are independent, if the CLs are independent, you don't recover. You have a very small chance of recovering as low a value of S1 half as you have. And then you discover that most of the time when you recover a low value of S1 half, it's for exactly the wrong reason. What actually happens is that you end up, by accident, doing something like this, which is very nice, but it's not what the data actually has. Okay? So 3% chance of recovering this low value of an S1 half, and a much smaller % chance of those actually having anything to do with the sky as we see it. So the translation is that the observed absence of large angle correlations is inconsistent at much greater than 97%. Actually, it's much more like 99.9% with the most fundamental prediction of inflationary cosmology, namely Gaussian random statistically isotropic ALMs. So the simplest hypothesis is that this is a fluke. You know, strange things happen. The moon is the same size as the sun. No one goes and explains that. It's just a fluke. Now, remember that you can say that it's a posteriori, but it's not really. What do I mean by that? I mean that we saw this in COBE. Right? We saw it in COBE, and with the error bars of COBE, the significance was about, the p-value was about 0.05. Okay, so if this had really been a statistical fluke, when we went and measured it with higher precision, with WMAP and then Planck, it should have stayed around 0.05. But it's gone from 0.05 to 0.0002. So that extra factor of 200, that's a posteriori, that's a priori, not a posteriori. Okay? So, but still, the simplest explanation is that this is just a fluke. Okay? And so what we have to do is we have to either come up with, we could come up with theories that try to explain it, but in the absence of theories, we can at least try to test the fluke hypothesis. Well, how do you do that? And the first thing is to realize that now that we've measured the temperature sky and also the polarization sky as well, we should no longer make realizations of lambda CDM that only give us the right values of the parameters. In other words, we shouldn't just take the parameters and stick them into our codes and produce skies that don't look like the sky we see. Right? We should produce skies that are the sky we see and let other things vary. So a step towards that is to make what we call constrained realizations, which are realizations of best fit lambda CDM, constrained to have the CLs that we see within measurement errors. Now that will automatically give smallish full sky C of thetas, and then we constrain them. We throw away all the ones that don't have a cut sky S1 half less than or equal to the observed value. We should really only keep the ones that have very close to the observed value within measurement errors. Okay? So instead of just making 10 to the 5 realizations of lambda CDM or however many, you should constrain them to have the properties that we see on the sky, namely the observed CLs and anything else that you think is appropriate. And in this particular case, the lack of two-point correlation. Okay? And then we can look at those realizations and augment them with other physical quantities with the correct covariance, like polarization and lensing potential and anything else. And we will predict that we get slightly different things than we would other times, without that. So for example, in unconstrained lambda CDM, here is the prediction for, was this the TQ 2-point S1 half, the S1 half of the TQ 2-point correlation function, where T is temperature and Q is the Q mode of the Q Stokes parameter. Okay? Or we could look at temperature lensing potential correlation functions and notice that they change depending on whether you look at unconstrained lambda CDM, which is what we're used to doing, or constrained lambda CDM, where we constrain the sky to look like our sky. Okay?
So we adjust the power interpretation. We're doing the CTE at large angle.
Yes. That's a good question. Let's talk about that. I think we're using standard lambda CDM, so I think the answer is no, because we're just saying that you're saying that there's I don't think the first few multiples have much impact on the value of much impact on the value of tau, but we should talk about that. That's a good question. Okay, so we haven't refit the parameters. We've just taken the parameters are really the MCMC chains and said, okay, but we're going to only allow those realizations that look like the actual sky we're seeing. Okay. Because I think you've extracted the correct value of tau, assuming that this is just a fluke realization. That's the assumption here, that this is just a fluke realization of lambda CDM with the best fit parameters. So. And we want to see, is that a correct assumption? So you can predict TQ and TU Here are ones that may end up being the most interesting, the QQ correlation and the UU. One thing you notice is that you predict that they won't generically be zero. Okay, that the QQ correlation and the UU correlation won't generically be zero. Now that's interesting because most physical explanations you can imagine. So suppose that what we see in an absence of a two-point correlation function, the temperature, is really physics, not fluke. Then what you'd think is that it must be that points on the last scattering surface that are further apart than some distance, corresponding to the 60-degree angular separation, are physically uncorrelated, that the mechanisms of inflationary perturbation theory that we thought correlated them didn't work. They don't work. There's something about physics on those large scales which means that they're not correlated. In that case, we wouldn't expect the polarization to be correlated either. Okay, so we'd expect the QQ-UU correlations also to go to zero. Now that doesn't happen, and that's because the other contributions to Q and U to polarization, to E-mode polarization in particular, mostly come from from locations near the last scattering surface. They come from relatively large redshift. By large, I mean much greater than 2. Okay, so redshift 10, redshift 7 or 8. So you're reasonably close to the last scattering surface. So if it's really physical uncorrelation, then we would expect QQ and UU to probably go to zero somewhere around here. But that's not what will happen if this is just a fluke. If it's just a fluke, then QQ and UU should be quite different from zero generically. Okay? Now, I don't think now Zhiqi can't comment, but I don't think Planck is going to measure this. Okay, as far as we can tell, Planck does not have the ability to measure the QQ and UU correlation functions at 90 degrees. Okay? That will require the next. Pardon me? You can measure it, but your error bars will be too big to tell the difference from zero. At least using what we had as the published ability.
So the low L.
It really is dominated by the low L. Right. Right. Huh? Right. Right. So, and you think you will be able to that the error bars on this low L CLs will be good enough to measure the QQ and UU polarization cross correlation functions. Okay. So if they are known, when they are known, okay, if they're close to zero, that would be suggestive that there's real physical correlation. Okay, lack of correlation for the distances of this length, of this size. But if that's not what we'd expect in lambda CDM. So if it's a fluke, we would expect this to be different than zero. This is what we'd expect. Okay. Similarly, if you look at EMO predicted local EE or BB correlations, then you can also compute the distribution of S1/2, say for BB, and here is the prediction of the best fit prediction of lambda CDM, and you get some distribution here that is whatever it is. It turns out that interestingly the expected value is not the. Let's see. The value you get from the theory CLs is not the same as the as the mean value. But what's more interesting is that if you end up with a very small value, okay, which is again what you'd expect if you have lack of actual physical correlation on the last scattering surface, then that would be an indicator that the fluke hypothesis is incorrect. Okay, so you see that there's very few, it's very unlikely to get a very small value of S1/2. If you do get that, then that would be a suggestion that the fluke hypothesis is incorrect.
So, but how do you know R a priori? You have an independent measurement of R.
Yeah, no, you don't. So this is with R. This is with a particular value of R. So once you measure R, okay, and then if you look at the 2-point correlation function of S1/2, I mean, you can rescale this. This just rescales as R. Okay, this is just this is just I could put the R's straight into here.
But if S is plausible, then R stays 0, then you get no constraint.
Then you get no constraint. Absolutely right. Then you get no constraint whatsoever. So this is just saying that you can make, all I'm saying is that you can make, there are testable predictions of the idea that this is just a fluke, right? So even a fluke makes, the null hypothesis makes predictions that are testable. That's the point, okay? And some of them are testable imminently, like this one maybe, or the correlation between temperature and polarization, or temperature and lensing potential. These happen to be relatively weak predictions. In other words, you don't get a huge change between the unconstrained lambda CDM and the constrained lambda CDM. Okay? But these are relatively robust in that it will be very unlikely in lambda CDM, even constrained lambda CDM, where we've constrained to have the small TT correlation, to have the QQ or UU correlations be near 0. Okay. There's another prediction. So if I go back to what I actually told you, which is that the 2-point correlation function is 0, that's not actually true. It's not the 2-point correlation function. It's the monopole and dipole subtracted 2-point correlation function, because remember that the monopole is what it is. The dipole, though, is mostly due to our motion through the universe. Right? That is expected to be 100 times bigger contribution to the dipole than the intrinsic cosmological dipole. Okay, so we just subtract it. Now, we don't actually know what the underlying true dipole is. Okay? So the interesting thing is that in order to preserve the zeroness of that dipole, then you require the cosmological dipole to be about 100 times smaller than you might have guessed, than you might have predicted for C1. So if you just change CAM and run it including the dipole, it doesn't normally report the dipole, then you'll get a value of around 3,000 micro K squared, and it can't be bigger than about 200 micro K squared without spoiling the vanishing of the 2-point correlation function. It's not clear. The problem is it's not clear that you can actually detect the dipole, that you can actually separate the cosmological dipole from the Doppler dipole. Well, as promised, I expected to not tell you about some of the other things that I find intriguing, odd things. One thing I will say that you should be aware when experiments improve their systematics and improve their analysis and make anomalies disappear. Anomalies should disappear because we have more data and better statistics, or better theory. This has happened a couple of times where one instead changes slightly what one reports and discovers that anomalies go away. And in each case, I think they didn't. But to summarize, let me say that if you believe the observed full sky microwave background, then there are signs that the sky is not statistically isotropic. The quadrupole and octopole aligned with each other. Well, they're self-aligned, they're aligned with each other, they're aligned with the solar system. These are very statistically significant. There's at least one of those alignments that all by itself has a 0.1% p-value. Okay. The observed low fluctuations appear correlated to the solar system, but not to other directions. This could be a statistical fluctuation, but it's unlikely. It could be due to features in the inflaton potential, but it's contrived. Oh, sorry, this is the next one. Sorry. If you don't believe the CMB inside the galaxy is reliable, then, well, It lacks large angle correlations. This was first seen by Kobe at the p-value of 0.05, but now has a p-value of less than 0.001 and probably more like 0.0002. Okay. This could be due to statistics, but it's unlikely. It could be due to a feature in the inflaton potential, but not only is that contrived, it doesn't actually explain away the problem. It could be due to the topology of the universe, but we have very, very good limits on that. Okay. So while the cosmic orchestra may be playing the inflation symphony, somebody seems to have given the bass and the tuba the wrong score, and they're trying very hard to hush it up, and there's no good explanation for any of this yet. Thank you.
This S1/2 is integral of C of theta squared. It is a 4-point function of the actual map at the end of the day.
Right.
So what you're saying over there is that the Gaussian energy does predict 4-point functions, and they never end up that small. That's
correct.
Actually consistent with the 2-point function.
Yes. Yeah. They're the wrong function of the 2-point function, and they never end up this small.
But
right.
why wouldn't that show up in the test of the large-scale non-Gaussianity in the 4-point as well? People do these tests on composers, but maybe they pick the wrong flame, or does that mean there exists a better flame to do these tests, which would give you a significant non-Gaussianity then?
Well, well, the other question is how, so, so many of the tests for, various deviations have most of their statistical weight at larger L, right? I mean, remember that the number of L's goes as L squared, the number of ALMs goes as L squared, the number of 2-point things goes as L to the 4th. The number of 4 points goes as L to the 8th. So it's very easy to underweight, to not weight this stuff and weight all the stuff at higher L's, which seems to agree much better with our theory in so many ways, right? So, I mean, I didn't talk about the little dips at the dip at L at the first peak and some of those, which also seem anomalous in interesting ways. But for the most part, this stuff up here seems to be Gaussian and statistically isotropic and all those things. And the stuff down here, below L of 50 seems to have all these odd things happening. And is it just our ability to see patterns, or is there really something strange happening at low L's? And then you have to focus on low L's if you're not going to be overwhelmed by just the number of large L ALMs. So I suspect that that's the reason why it's not picked up normally. Yeah. I'm here.
C of theta, the 2-point correlation, the base of points are correlated.
Yes.
Right. And when you square them and sum them up, so S halves, that is
right.
what you're looking at, the sum of a bunch of correlations.
Absolutely.
Right. Now, if you take the correlation into account and redefine the S half, then you get a number. The significance go down.
Sure, but I can invent all sorts of statistics which will be less anomalous. So so in other words, you're telling me that there's another statistic that's not as anomalous. I agree. For example, I can take the full sky reconstructed 2-point correlation function. The PCO, the MLE, maximum likelihood estimate of the the CLs. Turn that into 2-point correlation function. I'll get something that's much less unusual. Okay. However, so
I guess what I'm saying is that if you take the same statistic, but just remember that what you're summing over is a bunch of correlated data points. And take that into account.
But that object that you're describing is not a local measure on the sky of correlation. It's a different synthesis of the points. It's not the 2-point correlation function. It's another object.
What Amir is asking, I think you didn't take that into account. Is that when you calculate the likelihood of S, you didn't just blindly sum up the Gaussian points on the bill, you actually Monte Carlo this.
Yeah. So this is this is a statistic, right?
It includes all the
Right.
that are accounted for.
Yes, exactly.
It's an ad hoc thing to define, but somebody else defined it, or maybe he did many years ago.
No, someone else defined it many years ago.
Exactly, and then he just said, okay, let's stick to this. It's a bizarre estimator, or what bizarreness is not. It's a static thing, and just say, okay, I can Monte Carlo it, so the statistics may
Correct.
be complicated, but it's just very unlikely.
Right.
And that correlation is taken into account
Exactly. Yes. Absolutely.
We can talk about it now.
Yes. No, I remember your paper describing all this, and that you're right. That is a better estimator of something, okay? But it's not a better estimator of the two-point cut sky correlation of this object, this statistic, which someone else defined, in 2002 or 3. That's this object, and all we do is Monte Carlo, as you say, Monte Carlo that object exactly. Do exactly the procedure of observing the sky with these.
Right, but that person who designed this, he looked at the two-point correlation and said, oh, this looks bad, and let me sum these up, and then he wrote it as intriguing feature.
Very good, exactly. So, but this is exactly how people discover things, right? They look at data, they say, oh, there's this weird thing, okay? I'm going to write a statistic for this weird thing. This thing is weird. Now I have to go collect more data and discover, was it just that I saw this weird thing, or is it? So what's unfortunate is that, when the Kobe people published their graph and noticed that the two-point correlation function was small, they didn't say, okay, we promise to use this statistic forevermore to measure it. Okay? But you look at that and you write down a simple statistic like S1/2, or you can replace the square by a absolute or pretty much anything else, and you'll get a number, okay? And that number has gotten more anomalous by a factor of 200 since then, right? Now, you're right. We could have come up with good theoretical reasons why they should have come up with a better statistic. That's what you're saying. I agree. We could have. We didn't. They didn't. But now we could, and we discover, oh, well, that thing is less anomalous. I'm not sure, but it's a completely different statistic. Okay. So, that's why it's important. That's why it's important now to say, okay, what other predictions does the idea that this is just a fluke make? And you have to go test those. And every time you test those and find that that the fluke hypothesis fails, you gain more confidence that it's not a fluke. That's all. You still don't have an explanation, right? But this is how things start, where you have anomalous data and then you look for an explanation.
You should multiply your unlikeliness by about 20, because there could have been 20 other statistics that we just didn't publish because they were normal.
Yeah, but no, there weren't. But there weren't. Because everyone adopted that first statistic as soon as they used it, right? Right.
Statistics that you could potentially calculate is a lot larger than 20.
Yeah, I could multiply by an infinite number.
So I would argue that this number that everyone keeps talking about, 99.99% or whatever, is relatively meaningless.
So if you want to be
That it points to an intriguing thing to look at. But I think if you want to quantify something, you have to have two models that you have.
Okay, yes, I know you're being incredibly Bayesian, and I understand that. But on that basis, you also wouldn't believe in. You would only now be starting to be persuaded about the existence of acceleration. So, so it's valuable to be Bayesian, and that's a very useful perspective. But on the other hand, sometimes, often discoveries happen by frequentist approaches to data as opposed to Bayesian approaches. And then we go ahead and we do model comparison. And
I entirely believe that it points to an intriguing thing, and it's worth looking at it and building models.
Good. That's all I'm trying to say. But if I told you that it had a p-value in lambda CDM of 0.2, you wouldn't say that. So I have to calculate some number and show it to you, right? And now we can decide on the interpretation of that number, right? If I told you it was 0.2, you wouldn't, not 0.2%, 0.2, you would probably not be, you would say, well, why are you wasting your time? Okay.
Okay, so obviously we can continue that discussion upstairs.
Great.
So that's time for us again.